Alright, that last video got a little long, so we'll throw the last one in on this. Just like when we did a tangent line, for this we need an external point. I'll call it A. But what we're looking at is what's called a secant line. And you'll see that spelled here in just a second. But a secant line passes through an external point and intersects with the circle twice. So here we can see line AD is what we call a secant line. So here we go with a formal definition. A secant line is a line which intersects a circle twice. And I write that definition this way so that you can compare that to a tangent line, which just intersects the circle once. The secant line will actually enter and travel through the circle, so it will intersect it twice, once when it enters the circle and one when it exits the circle. Also notice that a secant line is related to a chord as well, because if you were to cut off the secant line at those points where it touches the circle and ignore anything out here, B, A, and on, then part of a secant will be a chord. So every secant is going to contain a chord. Alright, that's pretty much it for a secant line as far as definitions go. There are some nifty, handy-dandy facts that you need to know about a secant line, though. And let's start by taking a secant line and another secant line that both pass through the same external point, much like we saw with our tangent lines earlier. So what happens here is we have two secant lines passing through an external point, and just as before, when we had two chords crossing, if I were to connect these, what I would be making would be two similar triangles. So triangle ABE would be similar to triangle ADF. And since they're similar, I can set up a proportionality of the size of this thing. And so it essentially looks like this. If I have segment AB and I multiply it by segment AD, it's going to be equal to segment AE multiplied by segment AF. And of course I mean the lengths of all those segments. So if you look, this is zero different than our chord theorem that we talked about a moment ago. If we take the shorter part times the longer part is equal to the shorter part times the longer part. So that proportionality is still exactly the same as we saw with the chords. It's just now the intersection has moved to the outside of a circle. So these still are divided into proportional parts. Alright, another part we have to, or another nifty thing we need to look at with secants is what happens if we have a secant and a tangent line that come from the same point. So I'll put another external point out here, we'll call it A as well, and I'm going to draw one secant line through A, and we'll say that it intersects at BD. And then I will draw a tangent line also through A, like that, and we'll say that this is tangent at point F. So F is our point of tangency. So now I have a secant and a tangent line passing through the same external point, and an interesting thing happens here is that we're still looking at the proportionality between the short segment and the long segment of the secant, but what we find now is that the length of the tangent is the geometric mean between those. So when I set up a ratio to talk about this, I can say that if I take my short segment divided by the length of the tangent segment, so I know this is confusing with those segment bars there, but this is our divided by symbol there. So AB divided by AF is going to equal to, well, if AF was the geometric mean, needs to be across from each other here, AF divided by AD. So short side divided by the tangent is equal to the tangent divided by the long side, AD. And this is going to always be true when you have a secant and a tangent. The length of the tangent segment will be the geometric mean between those two.